Welcome everybody to Plants Cannabis Processing Talks here in April 2026, our 26th episode. We're very excited to have Alex Siegel on from Better Flange SPD to talk about the extraction tracker, incredible new analytical tool for midstream in-process monitoring for butane extraction, getting some amazing data. So Alex, do you want to introduce yourself and how'd you get into the industry and how'd you get to this point?
Yeah, thank you for the kind words, Emmett. I'm a cannabis processor that got into equipment sales through short paths, just developing stainless steel short paths with a company called Better Flange SPD. And more recently, I've been working on these sensors to try to give extractors a better idea of what we're extracting and try to get a good idea, some analytical data live while we're extracting of how much THCA is in our solution and how much contamination we're pulling along with it. The hope is to give operators the tools that they need to just make better decisions in the moment. There's not really any automation to our systems at the moment, but we are really just focused on giving the current lever turners better data, better solutions forward for maintaining productivity and efficiency in their labs. So the best way we found to do that is to detect THCA coming right off of an extraction column. And we developed a sensor to give high pressure hydrocarbon extractors a way to do that. So
that's great. And my question looking at this is, okay, who's this for? And it sounds like, high pressure hydrocarbon extractors is definitely, where you've done the calibration and developed the product for. But, is there a specific kind of processor that you think would most benefit from this?
Yeah, just really anybody who is kind of operating in a market where efficiency is super important. If your lab is turned off half the time, it's probably not as important for you. But if you are operating on a consistent basis, then the 10 to 25% or even more sometimes efficiency boosts you can get by optimizing your solvent use using one of these sensors is really can save you money and time over the short term and long term. Just being able to, in the moment, determine how is the product feed variability, how is the variability in your product stream affected by your process is really helpful. And I think that's something that almost every lab, even if you aren't operating at full capacity, you don't necessarily have consistent input material to your process. There's a lot of product variability in the market. So whether you're, if a lab is designing their process to extract, say, 15% material and the lab is seeing anywhere from 10 to 20% THCA in the input trim, then you're going to have variations in the process. And if you can't respond to that and create new recipes in the moment, there's efficiency that's lost by over extracting low potency material or under extracting high potency material. So it's really for anybody who has variability in the input material to their extraction setups.
Right, and in our demo lab here in Hillsboro, Oregon, we had opportunity to test the extraction tracker and see some live data. We're very excited to get one more permanently in our facility because, for us doing lots of bulk processing, large lots, but doing toll processing, so very variable feedstock. And so you really want to know, am I leaving any cannabinoids behind? Am I getting everything out of the biomass? But also, you don't want to just throw tons of solvent at it, because the more solvent you throw at it, the longer it's going to take to recover, and potentially the more solvent you're going to lose in the process as well. So, time is money and consumables are money. So bringing those costs down in a highly competitive market is really everything. So this is thrilling.
Yeah, absolutely. And even just having, you're in your situation where you have up to a 50-pound batch size. I don't know how often you guys extract exactly 50 pounds, but whether you're extracting 25 pounds, 35 pounds, or 50 pounds in your extractor, it's going to affect the amount of THCA coming out in any batch. And so you don't have to do any math, you don't have to do any calculations or alter your process really for when you have variable batch sizes too. You just watch the sensor for when THCA is no longer being extracted, and you're done. So it really removes a lot of the headache and a lot of the variability that comes with different batch sizes too. But also, I mean, testing variability, when you have a 50-pound batch, how representative is your testing going in as well? And it's in a lab like yours, you could have a huge swing in the amount of THCA in your extractor, depending on what part of that 50-pound batch was tested. So, you know, you're faced with spending money every batch on potency testing. Could be, what's a potency test currently in Oregon for you guys? Is it like $25 or $50?
Well, for research R&D testing, it's like, yeah, more in the $50 range. But the truth is, because of the turnaround time, more than anything in Oregon, in particular, most biomass coming to extraction actually isn't even potency tested. So you're really going in blind.
Interesting.
In a lot of cases, yeah.
So if you were faced with trying to optimize the setup, where you have, if you're extracting, in our hypothetical situation in this white paper, we said 3 batches a day. If you're doing $150 of potency testing a day and you're operating a full year, that's almost 40 grand in potency testing alone. So, you know, the ROI on a sensor that removes your need to do any pre-potency testing is, in that situation, is like 3 months or 4 months of just potency testing.
Right. And on the flip side, for operation in a state like Oregon is, you know, where you might just say, okay, we're not going to test, we're just going to run. Well, the result of that is you have to build your process around the sort of least optimal results. So you end up, you know, using more solvent than you should, or just spending a lot more time per run than you needed. Whereas with this, you know, you can just run it until it's actually done, and then, you know, cut off your solvent and minimize the total time, turnaround time, which is just incredible. It's going to be a big change for us.
Yeah, absolutely. Absolutely. Well, yep.
Yeah. So how do you do it? Like, how, you know, this is an amazing thing to be able to do, but like, you know, people have been trying to figure something like this out for years and years. And for us, you know, we've been in the equipment side of the business for, you know, 10 plus years now. And we looked early on at some process monitoring technologies somewhat similar to this, but using, you know, near infrared light. And you're talking $100,000 system just to get started, you know, and this is much more affordable than that. So how did you accomplish this?
Yeah, so just, you know, we started this project about 5 years ago, focusing on detecting contamination, detecting pigments in solution, and we just sort of slowly moved through the different iterations where it went from a tabletop tester to a high pressure flow cell detecting pigments. And once we had that ready to go, the market just really asked for THCA detection. And, you know, just kind of returned to the literature and purpose-built a sensor that we were hoping would work. Didn't work at all, and we adjusted everything, and, you know, went back to the literature, figured out a configuration that we thought would work, and it worked really well. So we just kind of brute force developed this thing, and it's been a 5-year journey here, but, you know, the effectiveness and the excitement from the market has definitely been worth taking all that time to develop it. So
amazing. And so essentially, fundamentally, what you're doing is you're shooting light at the actual solution that's coming off the process. So, you know, your extract in solvent, and then you're reading is it the reflection off of the stream, or is it, you know, what gets through the stream? Tell me a little bit about how can light actually even detect compounds like this?
Yeah, so without getting too much into like how an HPLC works, we have an input. It actually, I would call it like a digital sight glass, where you can imagine holding up a light to a sight glass and seeing through the sight glass and seeing how yellow the solution is. The sensor basically does that, but for THCA, and it's tuned for the correct wavelengths to be able to detect THCA in solution. Um, and it does that, you know, effectively, and we've been able to tune it for the concentrations coming off of an extraction column, as well as coming off of CRC columns, and more recently at your lab, coming off of a membrane filtration skid. So yeah, I would, if you're trying to think of how it works, I would say it works like a digital sight glass, where we shine light through the solution and we detect what comes out the other side.
That's great. And so the other big thing I noted about that is it doesn't require anything, you know, high voltage, or high
Correct. Yeah.
pressures, or you're not using a secondary solvent like chromatography analytical you would have to do. This is just like a light emitter and a detector in the box. Bring the solution in there, bring it out, and you can just get live readings. It doesn't really disrupt the process at all.
Yeah, yeah. So there's no electronics in the booth. All of the electronics sit outside of the booth, and the data is transmitted through some cables that are ported through the booth. Do you want to? Should I pull up the white paper to show
Sure.
the image? So what we have here is a white paper that can show some of the configurations of the sensor. Just to start really with the basic, what does it look like? We've got a sensor here on the right, this little box right here. I don't know if you can see my mouse, but I don't think you can. And then there's a cable that comes up and above and comes down to the electronics enclosure that's sitting next to a computer. And in between these two is a wall for your C1D1 control space, where, again, there's no electricity going through this cable. It's just porting through a fire hole in the wall that you install. We've got really only four pieces that you're thinking about when you look at this system. You've got the cables that carry the signal. You've got the flow cell itself, and then you have your electronics enclosure and your display. And those four parts make up the sensor hardware. And you just install the flow cell in an appropriate place in the booth where it can be accessible to the extractor, and then let it rip.
And it mentions here that could be a computer, but also could be a tablet. So, and does this require a wired connection to the electronics enclosure, or is there any way to wirelessly get this image if somebody had an explosion-proof, tablet or something like that?
Probably using the computer somehow to transmit the signal would be possible to use to have signal from inside the booth also. But yeah, for now, what I recommend is putting it on a table where you can kind of peek outside of the booth when you need to, in an area where you might be doing other work while you're extracting. Like if you have to walk past a certain area anyways to grab a consumable or grab a tool, put the computer there, and you can get a good view of what's going on inside. And it's kind of cool to be able to see, even when you're in a different place, is there nitrogen coming through the system? Is the THCA increasing or decreasing? And you don't even have to be in the room with it while it's doing that. So, or while it's extracting. But yeah, I would recommend aiming it in a way where you can easily see the screen from the booth. And I'm sure that there are screencasting programs where you could screencast into an explosion-proof tablet. But an explosion-proof tablet could be almost the same cost of this whole system in some cases. So maybe you have some better examples than I've seen in the past, but
it's definitely a few $1,000s to get into a real C1D1 tablet for sure. And there are some other devices that are a little smaller, a little lower cost, but I think it would mainly be if you had another reason already to have a tablet in there. You're controlling other hardware, but just good to know that there is the possibility for, if you had a large scale high end facility and they wanted everything at the point of use, that there's ways to get the data in there. And that's up to the buyer to make that decision. If you want that, we can make it happen.
Yeah. I'm sure that that is possible to do.
Okay, so you get this this data. You get this hardware installed. It doesn't require electrical in the booth, so you're really just dropping it in where you have access to the flow path of the solution after it comes out of your extraction column and before it goes on to whatever the downstream solvent recovery is or a tank. And then you're seeing readings coming off on your screen. How do you imagine that that's informing the operations? Is there just basically waiting to see line goes down, go turn off the valve? Is that the idea?
I mean, pretty much. It's the idea is that if the solution coming off of your column drops below a certain potency of THCA, then it's no longer worth it to extract that material further, right? And every lab is different. There might be some labs that make that cutoff at 2 grams a liter or 3 grams a liter, but for everybody, there is some amount where you could, if you wanted to do the math, you could figure out exactly when your lab is no longer making money by continuing to extract. But most labs, it's around 3 grams a liter or so where we've seen the cutoff be.
And if you
maybe
want
I
to
should
get
edit that out, actually. Maybe I shouldn't say exactly what the number is, but
well, that's all right. We can cut that out. But I can also just say, and if you're looking for specific data or an example, there's a great case study in the white paper that you can reach out to us at SciPhy Systems or at Better Flange SPD, and we can send that PDF out to you in the audience, and you can really get into the nitty gritty of the numbers. I think it'd be great to take a look at a little more detail at what an actual graph looks like. Would you be able to share a graph with us?
So what we have here is a graph that shows the data readout that the operator will see while operating the sensor. What you have coming from the left is the beginning of the run, and on the right, you have the end of the run. And you have 3 data points that are displayed in this graph here. You have THCA concentration in blue, you have pigment concentration in red, and you have a control wavelength that is affected by either of them in green. And what you can do is use this green line as a relatively stable control group that is consistently at the same light, the same amount of the same intensity. The other wavelengths are variable, and you can see by looking at the distance between these lines and the green line how much of those compounds there are. So in this situation, you can see that at the start of the readings, there was enough THCA that it was below the amount in the control or below the control line. So it was the pigment. But at some point, we did something. Maybe solvent continued to flow across the biomass. Maybe the material was just diluted. Maybe we added solvent to our material and it diluted. But you can see the THCA climbing, the signal climbing, which is associated with less THCA. And you also see that with the pigment. But at some point, we continue this processing, and at some point, something happened to the pigment where a significantly lower amount of pigment is in solution. And we can see that in this large drop where maybe we started a filtration, maybe we turned up a pressure in the membrane and the effectiveness went up. I'm not really sure exactly what happened, but in this moment, you can see that the pigment went from below the control line to above, and even above the THCA, and it stayed above the THCA as we went. And you can't really directly say that there's more pigment or more THCA. These are relative values when you look at them relative to each other. but the signal increasing or decreasing is a quantitative value. And when there's more signal, you have less pigment or less THCA. So yeah, the operator just follows this along and does, in general, will do things to try to increase THCA concentrations and decrease pigment concentrations until the end of extraction, when you start to see both of those things usually, but especially the THCA, start to drop in concentration.
Yeah, so when we look at the graph here, we have three colors. You've got your green, your red, and your blue. I heard you say that the green line is your control, so it should stay stable across the whole run. But what are the blue line and what are the red line, and what does up and down mean here?
Yeah, so the blue line is THCA concentration, and the red line is also is color concentration. When the line goes up, there's less of the compound. So as you see the graph increase, there's less THCA in this moment. Down here, there is more THCA at the beginning. After some time goes by, there's less THCA because you can see the graph slants up. And the same is true for pigment, where you can see the pigment, when you have more signal, you have lower pigment. So you have an example here where pigment jumped super quickly from higher pigment content to lower pigment content.
So the graph is showing how much light is getting through. So how much of that bright light is coming through. So the more obscured it is, the more colored that the solution is, or the more of the compound is in the solution, the less of the light gets through. So the lower the number is on the graph. And as you go up, it's getting more dilute. There's less of that compound in the solution. So essentially, when you're doing extraction, if you see the line, go up past the number that you've decided is your cutoff, that's when you would stop your extraction, stop sending solvent to your extraction run, and then fully push all the solution through your column and out into your collection vessel. What does the operator see when they're actually looking at the readouts, and how does that inform their decision making?
Yeah, so this is the kind of readout that the operator will have. They basically get a time trace of the concentration of compounds in solution, where in this situation, with the settings on the program as they were, the higher the level that's displayed in the graph, the less of a compound is in solution. So the operator is just watching those lines and waiting for them to increase or decrease to the set points that they have for their extraction. In this example, the blue line is THCA and the red line is pigment. And what you can see at the very start of the graph is a steep increase in signal, which correlates to a decrease in THCA. And you also have a decrease in pigment, as you can see an increase in the red signal as well. But as the run goes, you can see that the pigment had a large jump up in signal, which is correlated to a lower amount of pigment. And the THCA and the pigment then followed each other fairly closely for the rest of the run, generally increasing in signal and decreasing in concentration, up until the point where the pigment went off of the graph and we put the sensor into the lower sensitivity mode so that it can, the higher sensitivity mode, so that it could see the concentrations, even at lower concentrations of compounds. And you can see that at the end of the graph there, where the signals are no longer saturated.
That's great. And this particular run was actually measuring membrane performance, so a little bit different than what you might see on a normal extraction run. And we can look to the case study, the white paper, for a more representative graph of what an actual extraction run might look like. But the principle is the same. Down at the bottom part of the graph, you're going to have the highest concentration. So right when you start extracting, you might be at that highest concentration. Then it's going to go up to show that there's less concentration in solution. And once it gets up to that point, however high it is, indicating a low concentration that's not worth continuing to push more solvent through, that's when you can, stop your extraction process. So, oh yeah, and there's an example of the extraction.
This is another good example of what an extraction would look like, where at the beginning of the extraction, you can see that the concentration is just completely saturated, or the signal is completely blocked. And at the end of extraction, though, you see this steep line where THCA is decreasing in solution. And we go from this kind of higher concentration mode to a lower concentration mode at that point, where that graph shoots off into the top. And at that point, you can see a steady increase in signal associated with less THCA in solution. At the end of the run, you see nitrogen coming through. That's what all the mountains are at the sort of 3/4 way point in this run. And then you could see the further draining of some solvent after allowing the biomass column to sit for a few moments. And so you're going to see a continual decrease in concentration of THCA. And the operator, when they're looking at when do you cut off extraction, can just look at this graph. And when the solvent passes over a set value, then you stop adding new solvent to your extraction column, drain it, and move on to the next batch. So that's what the operator will see in general. And every extraction lab is different. Every lab would set that, that concentration where you cut off extraction at a different point. But it's always useful to have data and to know when these moments are where the concentration is significantly decreasing at the end of extraction. So
Great. Yeah. So, and of course, you're always working on the system, working with customers to make sure it's as intuitive as possible. And, I think from our brief time with it, we found it to be really, very informative for our process development. We're going to look forward to, generating a bunch more data, showing examples, and being able to show people live demonstrations as well. So really looking forward to having people get hands-on with this and get these out in the field.
Me too. Thank you for having me for those tests and those trials. That was a lot of firsts with the sensor, and it was really good to get some good data from those runs. So yeah, thank you for offering your lab space to us for those tests. Appreciate that.
Yeah, and we're really interested in the THCA side of this, but also in the other functions that the extraction tracker can perform with options. So you want to talk a little bit about what the options are and what the sort of use cases for each of those?
Yeah, so the extraction tracker has 3 main sensor options. You can detect THCA, you can detect total color, and you can detect the type of color, where there are some colors that look very similar to each other when they're in solution, but the pigment tracker, for example, is able to determine whether you're looking at chlorophyll or are you looking at a carotenoid. The color tracker, it tells you your total color concentration. It'll just tell you how much of the color are you looking at. And the THCA tracker obviously tells you the amount of THCA in solution, where the THCA tracker is focused on THCA yields, on minimizing solvent use, lowering your power use, getting more batches per day through your lab, and minimizing the need for potency testing. The color tracker is really more about lowering your pigment yield. You've got less need for crude purification downstream in your extraction process, and you really standardize the quality coming out of your extractor when you know how much color is coming out of your extract. And it allows you to really tune your media recipes for the total amount of contamination that you have going into the things like a filtration process or even a membrane filtration process. And the third option, the pigment tracker, is really just for pigment identification. If you want to know, do you have a pigment that is a antioxidant like a carotenoid, or do you have a pro-oxidant pigment like chlorophyll that will actually encourage your oil to spoil and doesn't have the kind of oxidative prevention effects as some of the other pigments have. So it really will help you identify when that's in your oil. It'll help you really fine tune your media recipes and ensure that you're not over filtering your material to where, if you want to leave a little bit of chlorophyll in your extract, you can do that and confirm that you're doing that using the pigment tracker. So those are the three options, and they can all be delivered in one sensor or one flow cell if a customer wants.
Right. So that would be, you have one box that you're passing a solution from one point in your system goes through, and you're able to, read up to 3 separate readings in that same box, just with the one connection out to your computer, and you can get all 3 of those data points. For us, I think really obviously the THCA application just makes perfect sense on your primary extractor. The output of your extraction column is a great place to locate that. Looking at the pigment tracker and the color tracker, that really made me think about batch testing for large operations. So for example, we have the small RH1 extractor that can run as little as 150 grams per run. Why did we make that? Well, for big operations that you might be buying 5,000 pound lots, from big farmers, or you might be, trying to determine, the difference between different products you could be buying, or just customizing your recipes on your processing to the incoming biomass. Being able to do a small extraction run, check your color coming off of that extraction run, and then use that to inform what your actual, your media mix is, or if you're going to take it to the membrane. It is huge, honestly. So on the one hand, might save you from buying bad biomass, but on the other hand, it lets you really tailor your process to what's coming in before you run any large batches. So I think that makes perfect sense. And then obviously us on the side of membranes, this allows you to actually see live, what is the color that's coming through off the membranes. What's the membrane actually filtering out for you? And then you can dial in your process as far as pressure, as well as the the flow rate, so that you're getting as little color through that decolored dewax membrane as possible. That's a game changer for us. Just being able to do process development and have that live feedback, really incredible, and means you have the highest quality possible product coming off, no matter what you're running.
Yeah, and it lets you compare batches between batches very easily, where you can compare what happened last time in your membrane. And when you do get a run where everything looks good on the sensor and everything looks good coming out of the evaporator, it makes it easier to have confidence that as long as you make it look good on the sensor, it'll look good coming out of the evaporator, and the operator can rely on that. It also lets you compare your process to other processes in general, where you might be processing with some CRC, and you want to compare how well does this do versus my membrane process, or vice versa. You can use the sensor to really directly compare what are you doing, and what did your inputs look like for those processes too. Like if you have the pigment and the THCA going into a process and coming out of the process, you have really strong control over what did you actually do when you extracted or when you purified something. So
and here's a big one that I just thought of is, if you had 2 points where you were sensing THCA in your process, or you had your piping made so that you could switch your input and outputs so that you're able to test 2 points coming into the same box, then you could see, are you losing THCA to your media, for example? Is it a concentration of THCA coming out of your media lower than it is going in? And by extension, what are you losing as far as yield when making that choice to use media versus not? I'd be really interested to see some of those results, and that's the kind of thing that we're going to be studying. I mean, we're just really interested to answer those questions, and The other thing is, it feels like media is, voodoo magic in a certain way, right? Right now, it's like, X versus Y versus, what company are you sourcing from? I feel like people have a decent understanding, but a little bit of it is just personal preference, kind of. It's more art than science.
Yeah,
This, with the pigment tracker, we can say, oh, this kind of pigment is absorbed more by X than by Y. So if
yeah,
you see that coming off of your extraction with this big lot of material, well, you probably want to use more of one versus the other, and be able to really change your mix up.
yeah, for sure. And without giving too much away, there is some the pigment tracker will do a ton of good for anybody doing CRC work, or anybody doing membrane work, trying to compare effectiveness of different processes. Even just the amount that you layer, whether you filter through one powder first or a different powder first, can really affect how effective those powders are. And you can see which ones, where if you put material on them that's too dirty, it loses its effectiveness at one thing. But if you're able to clean out, say, all the chlorophyll before you put your material onto this other powder, then it works a lot better to remove the red compounds. And if you just flip them, you don't get, all that you get is without the tracker telling you exactly what the pigments are, you just get yellow liquid. And, at the end of the day, you might end up with yellow liquid that reduces down to brown, and the next run might be red, and you're just questioning why. At what point in the process we have this contamination from a pigment, and was there a way to clean it up? The pigment tracker is really helpful for honing in on those things and optimizing things like just the amount of time you might spend media filtering, or the amount of time you might spend diafiltering in the case of a membrane. So yeah, highly recommended. I'm honestly, I find the pigment tracker to be as exciting or more exciting than the THCA tracker, but people want THCA, so that's what we've been focused on for a few months here, or a few years.
Well, it's really incredible to see just over that amount of time that you've been able to step up and really find a solution that works, and be able to diversify the capabilities of this system. I can imagine that that's only going to continue. I mean, you're getting amazing data. Be working with us and working with your clients, I'm sure, to build up a data set and be able to see, is there more that we could be seeing in here? Is there
Yeah,
a new type of sensor, or is there, even with the existing sensors, could we just change something up to see a whole other side of data that we haven't been able to do before?
yeah.
And to that point, how confident can people be that these results are accurate? How did you prove, and how, that this is a really reliable system, that what you're getting as far as the readings off the system is representing THCA, for example?
Right. Yeah, so THCA readings in the past, some companies have tried to detect it using standards that were liquid standards that something like an analytical lab might be using. But we just found that gives a lot of errors and poor results. So we always use solid standards, where we would take THCA diamonds and high terpene extracts where the contamination is, and we kind of broke down the samples using chromatography and using crystallization in order to isolate the components, and then put them through the sensor one by one to make sure that we are detecting what we think we're detecting. There's been a lot of correlation in the past where companies, create a sensor that might have an indicator that goes along with THCA some of the time, but in most situations, those indicators end up being purified out of our extracts. And as you end up with higher and higher potencies, you end up with lower and lower signals. So our sensor is validated using solid samples and chromatographically separated compounds that are representative of the contamination and the THCA that we are detecting.
Yeah, so unlike some other attempts at getting something like this to work, in your case, you could take a solution of extract and then pure 99% THCA crystal, and dissolve that crystal into that known extract and see, oh, here it is. It's a 10% bump in concentration. We see 10% bump in signal, and I want to really say that kind of confidence that was going to happen, it has never worked for any other system that we've seen tried to do this.
Yes.
But this, it's working, it's replicable, it works every time, and you've done a lot of background work to make sure that's true.
Yes, we have, and we are going to continue. So it's, I want to be able to say that and have confidence in that for every single different situation. Right now, we've focused on extraction, and extraction and CRC, and we are just we're testing it, and we're looking for situations where the sensor kind of breaks down and stops working. And so far, the moments where it stops working have been kind of useful moments, if anything, where things like nitrogen are being pushed through the sensor and the readings go crazy, but that's kind of what can tell you that you have nitrogen going through your sensor. So there's things like that where, there was one time where we decided to re-extract some material, and we were expecting to really get out a significant amount of THCA. We thought that we were going to get, at least a couple 100 grams out of that batch. But what ended up happening was the sensor was indicating there was almost nothing coming out of the extraction column. And there was a moment where we thought maybe the sensor's not working right. Maybe even though it was re-extracted, we all really thought that there was going to be a good amount of material coming out. And it just turned out that at some point, one of the extractors said, well, we have to listen to it. Just shut off the solvent and let's see what comes out. So we did that. We listened to the sensor, recovered the solvent, and we got about 30 grams out of 100 liters of solvent. So in that moment, we were kind of like, wow, we have sensitivity down to 3 grams a liter, where we can still see that there's something there, but was very little. And realizing that was a powerful moment where it was kind of like, okay, even if we really are confident, everybody in the lab thinks that it's worth it to keep extracting, the sensor's telling you not to. And even the person in the lab who's turning valves could step up and say, like, no, it's time to stop. Like, they were the person who was most confident in the sensor, in a kind of interesting way. So that was a moment where I kind of learned to listen to it and to trust it more. And I think that operators will have those kinds of moments with it very quickly, where something that you thought was an efficient process just ends up being like, oof, let's do it a different way, because there's no cannabinoids coming out of the system. So
yeah, or even more importantly, on the flip side, that you might have been stopping extracting early and just leaving a bunch of oil in the material that you could be yielding. I mean, I think some people, especially running at ultra low temperatures, might find that they're actually leaving quite a bit behind that they thought they were having an efficient process, but you got substantial percentage you could be yielding. And maybe that might shift some people's minds finally from going crazy cold, -80, -85 C extraction, up to slightly warmer temperature, because that once you see that you're getting so much less and you're having to use so much more solvent, might really be an aha moment for people.
Well, I mean, there's definitely a loss of efficiency if you have to go cold and you have to do a large amount of solvent. Those two things, where you just have extra cold going into your system, are definitely something that you have to fight uphill against. On the flip side of that, though, the colder you go, the less post-processing a lab has to do. And so there's lots of labs out there, in my experience, that have just invested a lot of money into keeping things as cold as possible. And so, like you said, like, people are going to realize that there's a moment where, if you're extracting at -65 to -80, where it's just not worth it to keep flowing solvent over it. And if you keep doing that, you can lose, 10%, 20% of your time in a day. And yeah, and those efficiencies really add up over time.
10 to 20% of your operating, capacity, that could be an extra run every day. I mean, that's big money.
If you were to extract with, like, in the hypothetical in the paper, you have a lab that always extracts with 4 column volumes of solvent really cold. So a lot of solvent really cold. And what they find is that when you have 10% potent material, you use over a column volume of extra solvent to get only about 5 or 6% extra yield, versus if you under extract your high potency material, then you end up with a loss of yield. So if you take that 1 column volume from your low potency extraction and use it during your high potency extraction, you can end up with a boost of like 10% to 15% efficiency just by switching that column volume of solvent from one to the other. I think it was actually like 9% total, by just deciding to not over extract the low potency and keep extracting the high potency. But that was if you have only 1 batch a day of low, 1 batch of high, and 1 perfect batch. If you have, say, 3 low potency batches in a day where you over extract all 3 of them, then you end up with a day where you've produced significantly less material, and you've just produced significantly less material than you otherwise would if you were extracting with higher potency material. And if you backed off of that last column volume extra solvent, you could fit a whole nother extra batch in a day and end up getting that production level up to where it needs to be. Yes, there's more biomass input, so it's 40, maybe 400 pounds a day instead of 300 pounds a day, but at least the output material is giving you the amount of mass per shift that you need to be, cost effective in your operation.
Yeah, and for a lot of operations, I mean, the more biomass you can get through in a day, the better.
For sure.
That's the bottom line. And
that kind of has an assumption of yield in it too, right? Like if you have to get through 300 pounds a day, you have an asterisk there that says, and get at least a certain amount of yield out of it, right? Like you don't want to get through 300 pounds a day and get a 40% yield when you could have gone through 150 pounds in a day and got an 80% yield. Like, why not? And we're talking about yield of THCA in the thing, not total mass of oil.
right.
But the ability to add extra batches, and when you look at the numbers here, comparing the efficiency of that 3 batch a day over extracting low potency material, you end up with a 40% slower operation than if you extract it with the proper amount of solvent. So that was one of the bigger differences, because you go from, the amount of loss that you have is so small compared to the amount of time savings by using the correct amount of solvent. And that ends up with according to my numbers, like a 40% increase in your efficiency for the shift.
Yeah, which is incredible. I mean, that's like, totally business model changing, that just like shakes the whole foundation, makes a terribly unprofitable business into a winner all of a sudden, right?
Yeah.
And I think that one thing that you said really stood out to me, which is that, you proved to yourself that you had the accuracy, to have very low level detection of the THCA, and that for that to be accurate. And when you're running, for example, live resin, where you have just less oil in the total mass because of the water weight, right? You're going to have lower concentration coming out, but the system's going to be able to detect well for that. And on the other side of that, also, it can be very hard to know exactly how much solvent you should be using in live resin, because of the variability in terms of the concentration of oil in the fresh frozen with the water weight is much higher. So for people that are running high-end live resin, where one, the value of the output product is much higher, but two, the variability of what is actually going on in the feedstock is so much higher. Being able to actually know when you're stopped getting oil out, and even if that total concentration in your solvent is lower from the get-go, that's huge. I mean, if you get an extra 10% of live resin out run on run, I mean, that's big money.
I hadn't even thought about that. The water is another level of feedstock variability there, and that makes a lot of sense. So it's like it's like an extra level where you have this higher quality product, and then you have this extra wrench that gets thrown into it with you got to figure out how much water you have. And on top of that, live resins are sometimes lower pigment oils, so the indicators that an extraction is done, the classic ones where you're looking for yellow on a site class, might not be as easy to follow when you have nicer material like that. So that's a great example.
Yep. And they also, for folks that are running systems where they don't have super efficient, cooling capacity on their extraction columns, they're also racing against time, so they really need to know when to stop flowing solvent into the biomass, because they don't want to let biomass warm up. If even if you're running really cold solvent, you don't want to run too much, because it could really reduce the quality of a output material that could be really top notch, top value. So really exciting for folks that have that as their business model as well.
That makes a lot of sense.
Great. Well, this has been an amazing talk, Alex. Thank you so much for coming on with us. Is there anything else that you're looking forward to getting more data from as we start to work together more out in Hillsborough at our demo facility?
I'm definitely looking forward to getting some more membrane data with John, and just seeing what comes off of your extractor too. Both of those things I think are really interesting. You guys do some of the biggest batches that I've ever experienced in the cannabis industry. So it's being able to handle the variability for a lab like yours is definitely a feather in our cap if we can get there. So
absolutely,
love to be on the cutting edge of that.
Makes a big difference for our bottom line, that's for sure. And it really also can't wait to show people with hard data that this is the comparison between running media versus running the membrane. And here's, if you use 10% of the media you would have used otherwise, that gets you to exactly the same place you would have been if you had used 10 times as much. That's huge. And then comparing that to just straight out of the membrane, I mean, this is going to be a game changer for us. It's going to be a game changer for a lot of our clients, a lot of people out there in the field. So really thrilled to see this product coming out. So last item to cover here, how much is this going to cost approximately, and how do folks get in touch with you?
Yeah, dude, thank you so much for all the kind words and for having me on this podcast today, for having me out at your lab. It's been really helpful for the overall process, just confirming the things that we are seeing in our own space. Confirming what we're seeing and more in another lab is really helpful and essential to the process of getting it into more and more extractors' hands. We can be contacted through Instagram is kind of the best way, or through our website. The website is betterflangespd.com. The Instagram is Alex Siegel 94 or Pigment Tracker. It's Pigment_Tracker. But the Instagram page is open. There's all kinds of data and examples on there that you can check out about the sensors, and feel free to reach out to me there. The sensors are aiming for around a $10,000 to $15,000 price tag, depending on the options that you go with, whether it's THCA or pigment or all three, or color or all three. The price is going to be around $10,000 to $15,000 in total. So.
That's great. And of course, you can always reach out to us at SciPhy Systems, at SciPhy Systems on all the platforms, or you can also reach out to info@SciPhy Systems for follow-up. We'd love to talk to you about this product as we start to roll it out with our product lines as well. And really look forward to an update sometime in the next few months after we've gotten a bunch of hours into this, and we can share even more information with folks from live actionable data. So thanks again, Alex, for joining us. It's been great. And please, everybody watching, like, subscribe, post a comment, hit that bell. We always have really great folks coming through for the best in technology in the extraction and processing side of the cannabis business. Alex, can't wait to see you again sometime in the future.
Thanks a lot, Emmett. See you soon.